In this video, I'm going to be taking you through a vapor compression refrigeration example. This one is just a basic cycle. If you need to see the first values, the starting values, just pause on the beginning. But we're going to get right into it. So we're beginning with state 1, which is going into the compressor. And so we know that the first pressure is 10 psi. And the temperature is 0 degrees Fahrenheit. And so, since we know these two values, we can fix state 1. And so we have to first find out where it's at. And if you look in the table, you will see that temperature 1 is greater than the saturation temperature at the pressure 1, which means that this is a superheated refrigerant, which means we use the superheated tables. I don't remember which one that is. Give me a second. I'll pull it up since I have the book handy. But it is table 10E since we're in English units. And well, that's the saturated tables, but the 12E leads you to the superheated tables for 134. And if you go to the superheated tables, you will find that an enthalpy value of 102.94 is received and an entropy value of 0.2391. And so we move on to state 2. But for this one, there is a compressor efficiency. I just forgot to list it at the beginning, so that is why we're solving for state 2s. The compressor efficiency is 0.83, but that doesn't really matter for right now. So we use the relationship S1 equals S2S for a isentropic compressor. And then we go and check to see where state 2S is on the graph, or on the, on the chart, and you will find that it is a superheated mixture because S2S is greater than SG at pressure 2, which is 180 psi. Yeah, sorry if I got a little bit behind the video there, but at any rate, once you find that, you can go into the superheated tables and find that H2S is equal to 131.04 using that entropy value that you got from S1, or the first state, and the perfect state. And so, since we know that the compressor efficiency is 0.83, we are now solving for the non-ideal version of H2, which is just H2, using the compressor equation, which we've all seen at this point. If you haven't, you really haven't been paying attention, have you? And so, we know if you rearrange that equation, you will find that H2 is equal to 136.8 with a circle. Don't forget the circle. And then we move on to state 3. I'm back to circles now. I got off of squares, apparently. Back to state 3. So we know that T3 is equal to 100 degrees Fahrenheit, and pressure 3 is equal to pressure 2, which was 180 psi. At the beginning they gave us pressure 3 and pressure 1, but we know that those two are equal across the heat exchangers because we assume no pressure loss inside of them. So we know we have to find where this lies once again in the TS diagram, and if you go to the pressure table and you look at the temperature saturation, you will see that T3 is less than Tsat, which means it is a subcooled liquid. And if you recall, to solve for the enthalpy value of a subcooled liquid, you must look up the HF value, the enthalpy at liquid value, but it must be at the temperature listed, not the pressure listed, because the pressure listed will be wrong. And I make that well known right here. It's not a big mistake, but it's a very common one. And so if you do that, you will find H3 to be 44.23. All the enthalpy values are in BTUs per pound. I'm just not writing them because it's just a little extra time, and I'd like to keep the videos pretty short, much as I can at least. And so now, if you recall on the diagram, you know that state 3 to 4 is through a valve. And I know this is everyone's favorite part because H4 just equals H3 through the properties of the valve. But we know S4 does not equal S3. If you recall on a TS diagram, this drops from where it would be subcooled on the far left into the saturated region through the valve. So if you ever have to find state 4, it's like quality or something, you would have to use the H value to find its location inside the saturated region. Anyway, so solutions, we are now moving on. The first part is to find the mass flow rate of the cycle. And once again, I forgot to write something down at the beginning, but they gave us the Qin of the cycle, which means the heat removed from the refrigerated space, which was 8 tons of refrigeration. And so we are looking for units in pounds per second, pounds per minute, etc., pounds per hour, whatever you, for some time, right? And tons, we're trying to get this to work out in the units in the end, so we have to change this into BTUs, etc. So 8 tons, if you do the conversion right, tons to BTUs per minute is times 200. So we get 1,600 BTUs per minute since we have 8 tons. Right? And so then we move on to the next part. And since we know the Qin value, and we know the enthalpies across the heat exchanger where it's at, which is the evaporator, I do believe, we know that this relationship we know this one works, and so we can solve for the only missing value that we have. But only I was supposed to circle mass flow, right? And I think I get a little bit confused here. I thought I was solving for Qin, but it's late. You'll notice that whenever I upload it. But anyway, we're looking for mass flow rate, and mass flow rate is equal to the Qin divided by the H's needed to create that heat in. So, as you can see, mass flow rate, if you work it all out here, you get 27.3 pounds per minute is the mass flow rate. And now, part B, we are looking for the heat out of the system, which is at the top of the cycle through the condenser. Pardon me. And so the heat out is just denoted as H2 minus H3 times the mass flow rate. So this one's not very tricky. No conversions really. So the heat out is just equal to, oh man, what is this one? 2,000, 2,500, I think. 27. Okay, I think that's what it was. 0.2. I was sort of right. Story of my life, sort of right. Alright, and so that is the answer to part B. With a circle. Don't forget it. Part C. And so part C for this one is work of the compressor. Now the work of the compressor, this one is, they want us to turn it into horsepower rather than BTUs per minute or whatever, or BTUs per minute, because, well, they hate us. So we have to do a bunch of conversions. I think I'm going to write this part out. Whenever we have a very simple answer like Q out above, I'm not gonna write it out because that one's pretty trivial. but this one right here might take a little bit of doing to make sure it ends up in the right thing. And yes, that HP means horsepower, not the wizard. I guess horsepower is probably lesser known than him. He is the boy who lived, after all. And so we write this out. We have 27.56 pounds per minute times 60 minutes gets you to hours, and then 1 BTU per hour, or yeah, 1 BTU per hour time is 2545 horsepower, and that's like the whole thing. Like if you really wanted to make this like flow better, you would put the 2545 after the H2 minus H1, but I was a little worried I was going to run out of room, so I want to make sure I got that in there. But it all works out in the end. You wanted to get your mass flow rate in per hour, and then you would multiply by the BTUs per pound. You would cancel the pounds, BTUs per hour into horsepower, and you get that as an answer, 21.79 horsepower. And then part D. Part D is simply the coefficient of performance, or COP. So the COP, which is denoted as the heat in to the system divided by the work of the cycle. And for us, that is just simply H1 minus H4 divided by H2 minus H1. But for other cycles, if there is a turbine over there, you'll have to count the turbine, but not in just a simple vapor compression. There is not. For, I think, Brayton cycles, there are. Gas refrigeration, I guess. And yeah, I had to rethink here. I was like, let's use some more space. And so, COP to be 1.73. Alright, that is the end of the video. Thank you for watching. I hope you learned something. And yay. And see you next time.